Thank you for the introduction. So today I'll be talking about a more practical consideration for fault-tolerant quantum computers, and that is mainly the need and the means of synchronizing logical qubits. So I'll start with some brief background on quantum error correction and logical operations, and then I'll get into the what, whys, and hows of synchronization, which includes some synchronization policies, and I will end the talk with a few brief results. So in quantum error correction, we start with a noisy physical qubit. This qubit is not really useful. So in order to improve its usefulness, we take many such noisy physical qubits and we encode them into one or more reliable logical qubits. This encoding is dependent on the quantum error correction code you use. So some examples include the surface code, quantum low density parity check codes, and color codes. So once we've decided on a quantum error correction code, we can now run a fixed sequence of gates, which is called the syndrome generation circuit. After running this circuit, we measure a subset of these physical qubits. These qubits that are being measured are generally called check qubits, measure qubits, parity qubits, ancilla qubits. They have many names. But the measurement of this subset of physical qubits yields a binary bit string, which is called a syndrome. And throughout the course of the computation, this process is repeated time and time again. And this generates a lot of syndromes, which are then decoded to detect and correct any errors that could have happened. So naturally, once we have logical qubits, the next question is, how do we do computation with them? And so, for example, here, I'm trying to do a logical controlled NOT gate between logical qubits P and P prime. There are many ways of doing this. You could choose to do this transversely. Transversal operations, however, especially two-qubit transversal operations, require three-dimensional connectivity, which may not always be available to you. So the other way of doing, or one of the other ways of doing it, is lattice surgery. And this is what I'll be focusing on for the rest of this talk. And in particular, I'll be focusing on surface code error-corrected quantum computers using lattice surgery. So before I describe lattice surgery, let's look into what that abstract logical qubit that I was talking about earlier actually looks like for the surface code. So this is a logical qubit, distance 3 logical qubit. Every circle is a physical qubit. Every colored circle is a check or measure qubit, which generates the syndromes that you measure at every round of error correction. Now, within these logical qubits, we have a fixed sequence of gates. So this is the syndrome generation circuit that's inside a surface code patch. So now lattice surgery can be used to implement a variety of logical operations. I'm not going to get into the details of how those logical operations are performed, but I will talk about the two constituent operations that make up lattice surgery. So the first lattice surgery operation is a lattice surgery merge operation. What the merge operation is doing is it's basically fusing or stitching two logical qubits together into a single logical qubit. And the other lattice surgery operation is the exact opposite. It's a split operation. It's splitting a logical qubit into two or more logical qubits. So now let's get into the what of synchronization. What do I mean by synchronizing logical qubits? So, in all these theoretical texts and in an ideal situation, what's happening is if we want to merge the two logical qubits I have here, P and P prime, prior to the merge, everything is in perfect sync. All the gates in the syndrome generation cycle are being executed at the exact same time. And so at the end of the final round of measurements right before lattice surgery, what happens is in the merged patch, we start with the first layer of gates across both constituent logical qubits. So then the syndrome generation circuit would then go in a lockstep manner across the merged patch. Now. So lattice surgery has this requirement. Every logical qubit involved in this lattice surgery operation needs the gate schedules to end at the same time before the lattice surgery operation and start at the same time after, right after you've done the merge operation. But what if this wasn't the case? What if we had a situation like this, where there is now a skew between the syndrome generation circuits of the two logical qubits? So depending on your frame of reference, one qubit is ahead in its syndrome generation cycle and the other is behind. So how do we go from the situation on the left to the situation where we start with the first layer of gates across the merge patch at the exact same time? How do we synchronize the two logical qubits? So this is the synchronization problem that we looked at in this paper. And before I get into how you can synchronize logical qubits, let's talk a little bit about why the situation on the left could happen, why logical qubits could be desynchronized. So there are many sources of desynchronization. I unfortunately do not have the time to go through all of them, but I will focus on the most compelling reason. So in a universal fault-tolerant quantum computer, we need these resources known as non-Clifford states, or commonly known as magic states. So a dedicated region of the quantum computer would be producing these non-Clifford or magic states at any given point of time. Once they are produced, they can be consumed by your algorithm, by your program, using lattice surgery. So that's the context of why I've been talking about lattice surgery. So now there are many proposals on how these non-Clifford states can be produced. And I think the most promising candidate right now is this protocol known as magic state cultivation. The reason why magic state cultivation is promising is because it drastically reduces the physical qubit requirement for generating these non-Clifford states. And so it's really attractive, especially in the near term. So the cultivation protocol proceeds as follows. You start with a small color code logical qubit. You do an injection of a T state into this color code logical qubit using a unitary circuit. Now, this color code logical qubit is really small. It's not really resilient to errors. So the next step is a growth or cultivation phase, where the color code logical qubit is gradually grown into a larger color code logical qubit. And during this cultivation phase, there is a 1-bit classical feedback that's always required when you go from one growth step to the next growth step. And this is, again, this is a classical feedback operation. But now, most importantly, magic state cultivation uses post-selection, which means that during this process of injection and then cultivation, if any error is detected, you throw away whatever progress you've made, and you restart from the very beginning of the protocol. Errors are random. An error can happen at any point of the computation. So this non-determinism in when a non-Clifford state will be produced by the protocol will be a source of desynchronization in the system. And in general, there has been a lot of work recently about using heterogeneous systems. So by heterogeneity, I mean, instead of using a single error correction code in your system, why not use a combination of error correcting codes? The advantage of this, is that by using the good qualities of different codes at the same time, you reduce the physical qubit requirements for the same amount of computation. But the problem with this is that every error correcting code has a different syndrome generation cycle. So I've tried to show that with the cartoon on the right. And now, whenever logical information passes from one code to the other, there will be desynchronization. A classical analog of this is clock domain crossing. You have two modules that are working on two different clocks. And if data passes from one module to the other, synchronization is required. Okay, so now we've talked about why we will need synchronization for fault-tolerant quantum computers. Let's talk about how we can synchronize logical qubits. So to present some synchronization policies, I need to set up a scenario. And the scenario here is very simple. We have two logical qubits, P and P prime. They differ in their syndrome generation cycle times by some slack, some non-zero slack, which I denote as tau. Physically, what this slack looks like is a difference in the execution phases of the two logical qubits. So patch P, for example, is maybe in its final layer of Hadamard gates, while patch P prime is in the first layer of CNOT gates in its syndrome generation cycle. And our goal is to go from this desynchronized state into a synchronized state so that we can do a lattice surgery merge operation between P and P prime. So the first synchronization policy that I want to talk about is a very simple synchronization policy. It is to just keep running extra rounds until the qubits are naturally synchronized. Obviously, this is only possible if your logical qubits have unequal syndrome generation cycle times. If they have equal syndrome generation cycle times, no matter how many rounds you run, you'll never be able to synchronize them naturally. So in this case, assuming P and P prime have different syndrome generation cycle times, we can just run a few additional rounds. So we've run a total of X and Y rounds respectively for P and P prime. And now the qubits are naturally synchronized. A caveat of this approach is that you could require a lot of extra rounds before the two logical qubits synchronize naturally. So to kind of illustrate that, let's look at some data. So on the x-axis of this graph here, I have different combinations of the syndrome generation cycle times for P and P prime, and as well as the synchronization slack. And on the y-axis is the number of extra rounds that you would need to run for the two logical qubits to synchronize naturally. For one case, you can't even synchronize them. It's not possible to synchronize them by running extra rounds. For other cases, you will have to run a large number of rounds just so that the two qubits will synchronize. And this is not ideal because now you're slowing down your computation. So we need some more practical synchronization policies. So the next policy is what we call the passive synchronization policy. In the passive synchronization policy, we know that one of the logical qubits is ahead in its syndrome generation cycle compared and with respect to the other logical qubit that's involved in the lattice surgery operation. So all we do is make it wait right at the end of its final syndrome generation cycle prior to the lattice surgery operation. This is passively waiting, so there is no error correction being performed during this idling period, and so the qubit is no longer protected by error correction. There could be idling errors that affect its reliability. So, okay, is there a better way? Can we do better than just passively idle? And the answer is yes. And we call this synchronization policy the active synchronization policy. So in this policy, rather than wait passively at the end of end rounds right before the lattice surgery operation, why not slow the logical qubit that's ahead? Why not slow that logical qubit down gradually? So what we do is instead of this, long waiting period at the end of end rounds, we reduce the waiting period by some factor, and then we insert idling durations at the end of every round of error correction prior to the lattice surgery merge operation. Now, what we've done here is we've reduced the idling period by a factor of n. The total idling duration is still the same, but the key insight here is that by making every idle period smaller, by making every idle period and by distributing it among multiple rounds, you can actually reduce the impact of idling errors that will come up during the synchronization process. And after this, there is a natural extension to the synchronization policy, which we call the hybrid synchronization policy. So now, while we insert these idling durations at the end of every round, we also run a few extra rounds of error correction. So here I'm showing we've run n plus z rounds of error correction. So what that allows you to do is actually further reduce the idling period at the end of every round of error correction and also control how many extra rounds you're running. So if you remember, if you just run extra rounds for synchronizing the two logical qubits, there's no guarantee on the number of extra rounds that you need to run. But here we're setting an upper bound on the number of extra rounds that are run, and we're also reducing the total idling period at the end of every round to further improve the performance of the synchronization policy. So how did we evaluate all of this? So this is the framework that we developed. We used STIM. We implemented lattice surgery. We implemented lattice surgery circuits and any generalized lattice surgery circuit. So for example, here you can measure any of the 4 observables that exist in this merged logical qubit after the lattice surgery merge operation. We built a scheduling pass on this lattice surgery circuit that could identify idling periods, that could insert idling errors, and so that we could insert the synchronization slack tau into the computation so that we could account for all these idling errors that happen during synchronization. So the first set of results I have is the reduction in the logical error rate of by using the active synchronization policy compared to the passive synchronization policy. So the y-axis is basically the ratio of the logical error rates of the passive policy divided by the active policy. And on the y-axis is the different code distances over which we perform lattice surgery. So for a distance 15 surface code patch, we see a reduction of up to 2.2x. So this is great. But we can further improve this if we use the hybrid synchronization policy. So remember, in the hybrid policy, we're further reducing the idling periods at the end of every round, but we're also running a few extra rounds of error correction. So every round of error correction adds a little bit of, a little error to your total error rate budget. And so there's a slight trade-off here, like about how many extra rounds you run, how much idling duration you add at the end of every round. So there is a complicated, no, not complicated, but there is an optimization process for the hybrid synchronization policy. For brevity, I've kind of omitted that, but if you're interested, please read the paper. But the point is, by using the hybrid synchronization policy, we can expect to see an additional 1.2x reduction in the logical error rate compared to the active synchronization policy. And this final set of results is to just show the cost of synchronization. So yes, the active synchronization policy does well. It reduces the logical error rate compared to the passive policy. The hybrid policy also does well, but there is still a non-zero cost for synchronization. And I think this is a good motivator for future work in this space, where we acknowledge the fact that synchronization will be required for fault-tolerant quantum computers, but there is a non-zero cost associated with the synchronization process. So while we've worked on reducing the cost per synchronization, how can we reduce the number of synchronizations that you require for a particular program? I think that's an important research area, and I think these results should motivate that. So that brings me to the conclusion of my talk. So I've explained the need and the means of synchronization for fault-tolerant quantum computers. I have shown some synchronization policies, and while our evaluations were restricted to superconducting qubits and the surface code and lattice surgery, it is extensible to any other technology, any other code as well. Thank you.